Let's take a look at this statement. She is a student at U of V. Is this a statement, the way that we have defined it in the logic section a few lectures ago? Remember that a statement or a proposition is a declarative statement, which this is, whose truth value is either true or false, so it has to be determinable. Is this something that we can determine to be true or false? Well, it really depends on who she is. If she is me, then I'm not a student at U of V. But if she is a person who identifies as a female in this class, then this statement is going to be true. So here, she is our unknown. And in terms of English, she is what we would call the subject of this sentence, and is a student at U of V is what we're going to call the predicate in English grammar, part of the sentence with the subject removed. And in fact, this holds true in mathematics as well. A predicate is a sentence containing a finite number of variables. In this case, she is a variable because she has not been fixed yet. And that becomes a statement when specific values are substituted or fixed for those variables. So if we fix me to be the she, then this predicate will become a statement that will, in my case, be false. If we have variables, then we have domains for those variables, much like in pre-calculus and calculus when we're talking about functions. Here, the domain of a variable is a set of all the values that may be substituted in place of the variable. Normally, we denote domain by the capital letter D. And then we can talk about the specific values within the domain that make this statement true. That is what we call the truth set. The truth set of a predicate is a set of all the values in the domain that make it true. And normally, we denote the truth set by the capital letter T. So, in looking at our example here, what are the domain and the truth set? First of all, we have to determine the variable. We have already identified that the variable here is the she that has not yet been specified. So what is the domain? Meaning, what is the set of all the possible values that we can substitute for this she? And this is all the persons who identify as female. What about the truth set? The truth set will be a subset of the domain. It is going to be those specific objects, or in this case people, in the domain that make this a true statement. So in this case, it's going to be persons who identify as female who are also students at U of V. Let's take a look at the next example, mathematical in nature. N is a factor of 8. So this is a predicate because the truth value of this depends on what value n is. So n in this case is going to be our variable. Let's think about the domain and about the truth set. What are the values that can actually be substituted for n? Well, n has to be a factor of 8, so it has to be something that divides other things. And whenever we talk about factors, we talk about integers only. We're not talking about fractions as factors. Remember that the domain are all the things that we can reasonably plug in, but it could make the rest of the statement actually false. So what is the truth set of the statement? What are, in fact, the factors of 8? And we can list them. It's a truth set, so it's indeed a set. Factors of 8 are plus or minus 1, plus or minus 2, plus or minus 4, and plus and minus 8. So in both examples, notice that the truth set is the subset of the domain, and that is set like that by definition. Now, we already noticed that this gets to be a lot to write out. So for example, in my persons example, the domain was persons identifying as female, and my truth set was U of U students, again, identifying as female. So there are going to be common portions to all of these, and therefore, it would be nice to develop a shorthand for how to write these down. This is when quantifiers come in. We will start off with the universal quantifier. it is a V with a horizontal bar across, and we read it as for all. So it's really just a shorthand symbol for that. But once we put it to use, we have to really learn how to use it properly, how to read it properly, and how to prove things properly with its usage. So our first statement here is going to be a universal statement which has the following form. Let's read it together with our newly introduced symbol. For all x in the domain, property Q of x holds. So this tells us that something is true for everything in the domain because it specifically uses the universal quantifier, and this gives us a property for all of the elements in the domain that is satisfied. In order to prove a universal statement, so in order to show that it's true, we have to show that it's true for every single element in the domain. If we are to prove that it's false, we're going to have to find or prove that it's false for one or more elements in the domain. And in this case, we've already seen it before. This specific example of when the property does not hold is called a counterexample. So just to, again, emphasize the big difference here, proving something is true is quite onerous because we have to prove this holds for every single element. And very often we deal with domains that are infinite, so we cannot just simply ask every single element if the property is true or not. We have to come up with more general techniques. But proving that something is false is easier in the sense that all you have to do is find one, or if you want more, examples when this property fails for the element in the domain. Okay? Let's take a look at how we can take English sentences and rewrite them in the format of universal statements. First of all, the key to identifying if it's a universal statement or not is the actual quantifier. If we see all being used and something that is stated to be true for all the elements, then we know we're in the case of a universal statement. So let's take a look at this one here. All humans are mortal. So we know that it's going to be for all, and then it's going to be for elements of this humans set. Well, we don't have a shorthand notation for that yet, so let's define it. Let's say H is going to be a set of all humans. And then we have to think about what is the property that this statement is referring to. The property are the fact that they're all mortal, so this is going to be the Q portion of our universal statement. So now we can get to actually writing it down. So what we have is all humans, which means all elements in the set of humans. Again, this X is simply a generic representative. So for all X in the set of humans, let me emphasize the fact that this is some kind of generic representative. It can be anybody in the set of humans, and it has to be true for everybody in the set of humans. And what is the property that we're after? We're after the property of mortality. X is mortal. Okay, so the format is going to be for all X in some set, followed by the property that this X has. And then we can talk about whether or not this statement as written is true. Is it true that all humans are mortal? Well, as far as we know, yes. So I am going to say that this is a true statement, but I'm not going to write it down because I don't have a very rigorous way of actually proving this statement. Let's take a look at a more mathematical statement where we'll be able to actually identify its truth value with a little bit more certainty. All real numbers are even. Again, I know right away that this is a universal statement because it starts with all, or something that has to be true for all elements of a certain set. My set here are real numbers, so this is going to be my domain, and I don't actually have to define it separately because that is something that I already have the notation for. Remember that we identified R, the bold R, as the set of real numbers. And the property that I'm after, this Q here, is going to be the fact that something is even. So, writing this out in fully symbolic form, I have for all representatives, for all elements of the reals, X is even. Is this true or not? Is it the case that every single real number is even? No. How can we show that that's not the case? Remember that in order to prove that something is false, all we have to do is find one or more examples when this property within the reals fails. Well, there's many examples I can find. So the counterexamples that we can produce here are plentiful. First of all, we're talking about real numbers. So they don't even have to be integers. And there's the concept of evenness or oddness is only defined for integers. So for example, I can pick some number, 1.3, and it's not even. You can of course pick a integer number like 7, it's also not going to be even. That's why it says for at least one. My counterexample might be different from your counterexample, but it does not affect the falseness of the statement. As long as you can provide a counterexample, that is good enough to prove that the statement is in fact false. Let's take a look at the following examples. We have a set A, 1, 2, 3, 4, and we're asked to consider this statement. For all x's in A, so for all the elements in set A, x is less than or equal than 5. Is that true? Is it the case that for all the elements inside the set, that element is less than or equal than 5? So all the elements in the set are less than or equal than 5. Well, there's only 4 of them, so inspection works pretty fast. And yes, I can confirm that this statement is true. Now, remember though, in order for me to rigorously prove it, I actually have to go and check each single one of them. Now, there's only 4, so I can do it quickly. But nonetheless, if I am to write the justification, I'm going to say that if this is true, and we claim that it's true, so to show it's true, I will have to check each and single element. We must show this property holds, so the property being x is less than or equal to 5 for each element of A. So I'm going to actually go through each one. 1 is less than or equal than 5. That is true. 2 is less than or equal than 5. Also true. You know what? I'm going to skip the check marks, though my daughter loves them. 3 is less than or equal than 5. That's also true. 4 is less than or equal than 5. That is also true. I have checked them all, so I know that it's actually true for all of the elements in the set. And I can say that it's true then. Notice the difference between me inspecting all the elements here and me inspecting all the elements here. If I can go and talk to each and every single human on Earth, and they in fact confirm that they're mortal, I will be able to certainly state that this statement is true as well. Consider the set A now being equal to 3, 4, 5, 6, and we have the exact same actual universal statement. For all the elements in A, x is less than or equal than 5. Now, showing that it's true means I had to show it for each and every element in the set. Showing that it's false, and I believe that this statement is now false for this set, involves me having to find only one failure. Okay? So, to show that it's false in this case, I know that it might seem easy in these examples. Once they get more complicated, though, you have to remember that the structure doesn't change. To show that it's false, we need to find one element or more for which it fails. Okay, so what do I have in this case? What elements can I find here? Again, at least one for which this property does not hold. Well, I can see, for example, that 6 is in there. 6 is certainly not less than or equal than 5. So this is my counterexample. And this allows me to say that this universal statement is false. So once again, highlighting this fact here, I'm in fact going to keep my color scheme from above. Showing that something is true, we have to show that it's true for each and every element of the set. Showing something is false requires me finding one or more failures. Now, in this next example, we're going to try to go from the symbolic form to English forms, trying to see if we can spot whether or not these English forms are equivalent. So what do we have here? For all basketball players X is tall. Take a minute here and see if you can decide which ones of these statements are equivalent to this one and which ones you believe are not. So the statement is again, for all basketball players X is tall. Remember that X is just a generic representative. So what this is really saying is for all basketball players, they are tall. Every basketball player is tall. Indeed, that seems to be pretty equivalent. Among all basketball players, some are tall. There's a difference between some and all, and it's not the same. This says all basketball players are tall. This says some are tall. This is not equivalent. Some of all the tall people are basketball players. This seems a little tricky, and I'm gonna leave it to you with the following thought. What if the set of basketball players is empty? What happens in that case? Let's take a look at others. Anyone who is tall is a basketball player. Well, it's certainly not equivalent. This is saying that for all basketball players, so my domain is basketball players. Here, my domain is tall people. They have different domains. These are not equivalent statements. All people who are basketball players are tall. So the domain are the basketball players, and the property is the fact that they're tall. That is, in fact, the case. Anyone who is a basketball player is a tall person. Anyone who is a basketball player, for any generic representative of it, they are a tall person. So those are, in fact, equivalent statements. And here we go. Universal quantifiers are extremely useful. In shorthands, we just have to practice translating between the symbolic form of the statements and the sort of everyday colloquial formats, as well as being able to think about what are the differences between proving whether something is true or something is not true for a statement that is said to be a property of all of the elements in some set. The quantifier is existential quantifier. It is a backwards letter E, and we read it as there exists. Much like with the universal quantifier case, we have an existential statement that shows us how to use this existential quantifier. So there exists X in D, the domain of the predicate, such that a certain property holds. Notice the difference here. There exists an element as opposed to for all the elements. And this definitely affects the truth values of the existential statement. In fact, it will feel almost exactly the opposite. There exists is true if it's true for at least one element in the domain. After all, you just have to find the one that in fact exists. But in order to prove that this statement is false, you have to check it for all the single elements in the domain. You have to go through all of them to show that the property does not hold, and therefore the one that is stated to be in existence doesn't actually exist. Okay? So here we have that in order to show something is true, we need to prove it for one element, and in order to show something is false, we need to prove it for all. Let's take a look again at examples that are stated in English that we're asked to rewrite in the symbolic form. Some humans are blue. So there exist humans that are blue. The domain that we're talking about are humans, and their property is being blue. So as before, I'm going to let H be a set of all humans. And as before, using X as a generic representative, some humans means there exists some humans. So there exists an X in the humans such that, so we can have a comma or actually write out such that, either way works fine, such that X is blue. If I am to prove that this is false, which I believe is false, I'm going to have to go through all the humans and look at each one of them and determine whether or not they're blue. If I have gone through all the humans and none of them have been blue, then I can claim that this is in fact false. But until I've gone through all of them, I cannot guarantee that I just haven't met the one person that is in fact blue. Mathematical statements are going to be probably a little bit easier by comparison. Some real numbers are even. So again, we already have the notation for real numbers, so I won't have to define a new set. Some real numbers are even. So that means there exists some x in the real numbers such that x is even. All I am asked to show here is an existence. I have to show that a number like that actually exists, which means that one example will do the trick. And I have, in fact, many examples that I can come up with. So for example, x equals 2 is a real number and it is even. So I'm done. This is certainly a true statement. Just like in the last case, let's consider a set 1, 2, 3, 4, and let's think about what it means for this particular existential statement. For my set A, there exists an element of A such that x squared is 25. Is that true or not? I'm asked to show that there exists one. If I am guaranteeing that it's going to be true, I have to find at least one such element. If I am going to prove that it's false, then I'm going to have to go through all of them and show that it doesn't work for any single one. Now, again, the set is small, so just by looking at it, I can quickly check. So I'm going to write out the procedure. I believe it's false, and in order to show that it's false, I will have to check. We must check all the elements of A. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. None of them have square that is 25. So now that I have checked them all, I can guarantee that the statement is false. Okay? So again, just to emphasize, if I am to prove that an existential statement, so there exists an element, is true, then it has to be true for at least one such example. All I have to do is find one in existence. If I have to show that it's false, I'm going to go through all of them and show that there isn't one in existence. So all of the elements actually falsify this specific property. Let's take a look at an example where we are given the symbolic form and asked to determine whether or not these statements are equivalent to the one stated. So there exists real numbers such that x squared is 2. Let's see what we have in terms of suggested potential equivalences. The square of each real number is 2. That is certainly not equivalent. Here the statement is existential, here the statement is universal. There exists versus for all the real numbers. So this is not going to be equivalent. Some real numbers have square too. That is in fact exactly what the statement is saying. There exist real numbers, some of them, for which the square is equal to 2. If x is a real number, then x squared is 2. That's certainly not what this is saying. For some real numbers, it's true, but just because x is a real number does not guarantee the truthfulness of that statement. Number x has square 2 for some real number x. Sure, that is in fact very much equivalent to our original. Some real numbers have square 2. Oh, I do believe that these are the same. So yes, that's a freebie. There's at least one real number whose square is, and it looks like it got cut off, 2. Here we have to really think about this. There is at least one real number whose square is 2. there is real numbers such that the square is 2. Do you believe it's true or not? I'm going to leave it up to you to decide. Let's rewrite where we're given a statement and the beginning of the equivalent statements. For all objects j, if j is a square, then j has 4 sides. So for all the objects, as long as it is a square, it has 4 sides. All squares have 4 sides, right? If it's a square, then it has 4 sides. So all the squares have 4 sides. Be careful about whenever you're rewriting in terms of equivalences, not imposing your everyday logic on it. You really have to only work with what you're given and not what you want to be true about the world or what you know to be true about the world. Every square, well, if j is a square, so we already have that that's true. Every square has 4 sides. So we can, in fact, continue in a similar fashion here. All and every are equivalent. If an object is a square, for all objects, if j is a square, so if an object is a square, then the conclusion will hold. Then it has 4 sides. For all squares j, if j is a square, for all the squares, j has 4 sides. This is just to show you that given a seemingly specific existential statement, there are at least 4 ways to rephrase it in an equivalent manner. So if you write yours down in one way and your friend writes something down that looks slightly different, doesn't mean that one of you is wrong. You might actually very well both be correct. The universal conditional is, in fact, a statement of essentially this form. So we can generalize the previous example. For all x's, if p, then q. Universal is made by the fact that this is true for all elements x. There are many equivalent forms, and in fact, some of them are universal and some of them are existential here. So let's read through. For all x, if p, then q is what we start with. For all x in t, we have the property q. So t, remember, is the truth set of the predicate. So for all of the elements that already have this quality, we can conclude that q is the case, right? So maybe let me do this here. All of the elements that already have this property, the set for that is the truth set, t. For all x's, if x is in the domain, then the property q holds. The domain means that the property p is, in fact, imposed on the element x. If x is in the truth set, then q of x. This is similar to this one. This is now a little bit different, but actually, in fact, equivalent. There exists x's such that property p and q both hold together. This is saying for all x's that have the property q also have property, that have property p also have property q. This is saying that there actually are the elements that have both of these properties. And then this is, in fact, equivalent to this one. If there is or there exists element x in the truth set of p, so this property already holds because it's captured within t, property q also holds. And this is essentially rewriting both of these, but using the and for the notation. And now we are going to introduce yet another shorthand symbol that we're going to be using throughout. P, then Q, if we have a double arrow, we're actually meaning that it's a universal statement that is of the conditional format. So it's true for all x's that P implies Q. So to drop the for all here, we're going to introduce the double arrow. And we're going to do the double arrow in both directions if there's a biconditional on it here. So the universal biconditional, we're going to denote this way. The universal conditional, we're going to denote by a double arrow in this direction. Let's practice some more writing statements that are in plain English using formal logic. note that for some of these, you will have to come up with the definitions of the sets that you're going to be using. For example, anyone who studies math is happy. You will have to decide what is the set that you want to introduce. For example, people who study math. But for some of them, we're already going to be able to use the sets that have been predefined for us. For example, integers already have a notation. I suggest you pause the video here, take a minute, and try to actually write these out in the symbolic form yourself first. So some integers are even. Some implies that we're after the existential statement. There are x's that are integers such that x is even. So this is like an exercise in determining what is the set, what is the property that you want to hold, and whether or not we're after the existential or the universal statements. The cube of every negative number is negative. Every negative number, so for all x's that are negative numbers, so let's say we're in the reals that are negative, the cube is also negative. See how much shorter it became? I remember first learning quantifiers and the symbolic logic here, and I thought that this was a whole other language that I couldn't wait to actually learn. Funny story too is that my mom uses the for all symbol basically in everyday life. So if we go shopping and we have to buy both types of milk, lactose and non-lactose ones, she will literally write for all milks in her shopping list, meaning that we need both types of milks. Anyone who studies math is happy. True story. So here, we don't have the sets like before that have already been defined for us. So we're going to introduce our own set. So let's say that M is going to be a set of people who study math. I suppose it can be just a set of any living beings who study math, maybe not necessarily people, it says anyone. And then once we have defined our set, we can state what the actual property is. So for all x in M, everybody who studies math, they are happy. So x is happy. We can find a white rabbit. We can find means that not necessarily all of them are white, but we can find one that is white. So out of all the rabbits, there exists some that are white. Now, we don't have a set of all the rabbits, so I'm going to first define it, set of rabbits. And then, once I have that in place, I can translate this into the symbolic statement. There exists an element of the set of rabbits such that x is white. There we go. All elephants are gray. We have all, so this indicates the universal statements. Now, it's about elephants, for which I still don't have the actual set defined. So first, I'm going to say that E is going to be a set of elephants. And then all elephants are gray. For all x in the elephant set, x is gray. Each rain cloud is gray. Each of them, for all of them. Now, rain cloud is again a set I don't have, so I have to define that first. Let's say C is going to be set of rain clouds. And then I can say that each rain cloud, so for all x in the rain cloud category, x is gray. And this is important because notice that now I actually have both of these statements that look very much the same. So I have defined two different sets, the elephants and the clouds, but their properties are the same, and both of these are universal. This is essentially the strength of these types of things, is I can begin to notice structures that might not have been visible in terms of English because we would be hung up on the fact that, for example, these objects are living and these ones are not. If a book has no pictures, it is boring to read. So here we have an if statement that is a conditional, and we're talking about books with no pictures. So translating this into somewhat symbolic form, I'm not going to go all out and define all the sets of all the books and the sets of all of the books with no pictures. I'm going to make a very sort of economical, let's say, shorthand. For all books X, if X has no pictures, then it's boring. Now, finally, no dogs are pink. Now, so far, we don't actually have a way to deal with the negations. This is quite literally what we have coming up. So how can we translate that into a positive statement as opposed to negative statement? No dogs are pink means none of them are pink. So all the dogs that do exist are not pink. So just reasoning it out, we can see that we can transform this into a different statement. No, none of the dogs are pink means that all dogs are not pink. And now I have myself an universal statement. All dogs are not pink. So if I can define D to be set of dogs, I can then rewrite this as for all X in the dog set, X is not pink, unfortunately. And there we go. This, yet again, takes a little bit of practice, so make sure that you go through these types of questions and understand how to translate them from English into symbolic form. As we have just noticed, negations might be something very useful to have, and these types of translations do not come in intuitively. So let's see what are the actual ways that we can negate a universal, an existential, and a universal conditional statement. So the negation symbol is going to be the exact same one we've used before. If I start off with a universal statement, for all X in some domain D, property Q holds, negating it will actually negate both the universal statement into a existential, and it will impose the negation on the Q. So as I go through, the opposite of universal for all is actually there exists, and as we will see shortly, the opposite of there exists is going to be for all. So we simply flip from one to another. The negation of for all is going to be there exists, and then we just have to make sure that we negate through to the property as well. So we notice that this, in fact, is exactly what happened here. No dogs are pink turned into all dogs being pink. If we start off with an existential statement, there exists an X such that some property holds, and we have to negate that throughout, it's going to be the exact same thing. The negation of there exists is for all, and the negation of Q is not Q. Negation of a universal conditional statement will be very similar to what we've seen in the logic section. So the negation of P implies Q is actually P and not Q. And so all we have left to negate is this for all, which turns into there exists. There are a few exercises here to rewrite using formal logic and then negate. I'm going to leave these up for you as extra practice to fill in with the answer keys available. This is really excellent practice for using the actual for all, there exists, if, then, and also practicing your negation.